Up there, right now, circling our planet, are billions of dollars of our most advanced technology. Now, when we think of a satellite failing, we picture something big, right? Like an explosion or some dramatic collision. But what if I told you the biggest threat is actually a slow, silent decay, happening deep inside the machine where no one can see it?
Well, back in 2013, that's exactly what happened. It crippled NASA's Kepler Space Telescope, a $600 million marvel that had discovered thousands of new planets. It wasn't hit by anything, no spectacular boom. Something deep inside just gave up. So, what was the culprit?
All right, so here's what we're going to dive into. First, we'll uncover this hidden weakness that plagues so many satellites. Then we'll zoom right in on the tiny, microscopic cause, which is all about lubrication. We'll walk through the brilliant three-step solution researchers came up with, see if it actually worked, and finally, really understand why this is such a game-changer for space exploration.
You see, those big, catastrophic failures are actually pretty rare. The real mission killers? They're much quieter. It's the tiny, moving parts wearing out over years and years, thousands of miles away from any possible repair shop.
And get this, the Kepler failure wasn't some fluke. It wasn't a one-off thing. Just look at this list. From the BIRD satellite in 2001, to FUSE, to Kepler and the Dawn space probe, it's the same exact component failing again and again and again, the reaction wheel. This isn't bad luck, this is a pattern.
Okay, so what is going on with these reaction wheels? To get that, we need to zoom way in, down to the microscopic level. And it all boils down to one simple but crucial thing: lubrication.
But first, what even is a reaction wheel? Well, think of it like a satellite's balancing system. It's basically a flywheel that spins. By very precisely speeding it up or slowing it down, a satellite can turn and point itself. It's how a telescope aims at a star or how an antenna points back to Earth. Without these things working perfectly, most satellites are just very expensive, useless hunks of metal.
So here's where we get to the heart of the problem. Inside that spinning wheel are bearings, kind of like the ones in a car, and they need lubricant to run smoothly. But up in the harsh vacuum of space, that lubricant slowly but surely disappears. It evaporates or it creeps away. And both of these processes are driven by one single, absolutely critical factor: temperature.
And that leads to a pretty logical question, right? If temperature is the key to everything, why not just stick a thermometer on it? Just measure the temperature and keep an eye on it. Well, that sounds simple, but it turns out to be a massive engineering headache.
And this is why. Look at this model. Engineers can measure all sorts of things: the motor current, the wheel speed, the voltage, but you literally can't put a physical sensor on the lubricant that's inside a sealed bearing spinning thousands of times a minute in a total vacuum. It's impossible. So the one variable you need more than anything else is the one you absolutely cannot measure.
So, how in the world do you solve that? Well, when you can't measure something directly, you have to get clever. Like, really clever. Researchers came up with this amazing three-step method to basically create a virtual sensor, a way to see the unseeable.
This incredible work comes from researchers Alidadi and Rahimi. And their goal wasn't just to figure out what was going wrong. They wanted to build a predictive tool, a kind of crystal ball that could tell them the remaining useful life, or RUL, of these parts before they failed. And they did it in 3 totally brilliant steps. Step 1, they call it the temperature detective. The model takes all the data they can measure, like the motor current, and uses it to calculate a super accurate estimate of that hidden lubricant temperature. Step 2 is the degradation model. Now that it knows the temperature, it can figure out exactly how fast that lubricant is disappearing. And finally, step 3, the crystal ball. It takes that decay rate and projects it into the future to predict the exact moment of failure.
Okay, so this is what the actual research framework looks like. This first part here, that's the temperature detective. You can see all the sensor data they can get: speed, current, going into the model. And what comes out is that reconstructed state, that crucial temperature estimate. That's step 1. And this shows us the rest of the magic. That temperature from step 1 feeds right into step 2, the degradation model. And then all of that gets fed into step 3, the prognosis, which spits out the final prediction, the remaining useful life. It's an incredibly smart and elegant solution.
So this all sounds amazing on paper. It's a fantastic theory. But the real billion-dollar question is, did it actually work?
Oh yeah, it worked. And how? In their test, the model's prediction error was as low as 0.1%. That's an accuracy of 99.9%. I mean, that's not just good.
For a system this complex, flying through space, that is practically sorcery.
And they didn't just test it on one simple scenario. Nope. They ran it against two completely different types of faults. The first was just predicting normal wear and tear, when the lubricant would naturally run out. But the second was way more complex. They simulated a failure in a backup system that was supposed to add more lubricant, and the model nailed that one too.
And you know, the researchers themselves put it best. This quote says it all. Having this prediction allows the satellite's operator to manage what the satellite does with the time it has left. It completely increases the chances of a total mission failure becoming a partial one.
So what this really does is change the entire game. We're moving away from just waiting helplessly for a satellite to die and into a new era of what you could call managed degradation.
And the impact here is just immense. This means we can save missions worth hundreds of millions of dollars from just suddenly ending. We can squeeze every last bit of science and value out of these incredible machines. Operators can decide, okay, let's get the most important data right now while we can. A sudden total loss becomes a planned partial one. And maybe best of all, it gives engineers priceless data to build even better, tougher satellites in the future.
So at the end of the day, this isn't just some clever fix for one little component. It is a massive step towards making everything we do in space more resilient, more efficient, and way more sustainable.
Which, of course, leaves us with one last big thought. This idea of using the data you can see to predict the failure of something you can't is such a powerful concept. If we can do this for a tiny part spinning in the vacuum of space, what other complex failures could we start predicting right here on Earth?